Click them closed, have a look. We'll finish up this one quick problem from yesterday. And then I got to show you something else. All right, so we were doing U substitutions, right, on something like this. And what are your thoughts when you look at that integrand? Looks terrible. Okay. I mean, what integral standard form does that start to kind of look like? It starts to look like an arcsine, doesn't it? Right? Because it looks like 1 minus, I've got an x squared there, but I could turn that into, by making a u substitution, I could make that look like the square root of 1 minus u squared, which is my goal. Yep. Right there. There you go. Mm-hmm. So that's what we did, right? We said, let's let u equal 8x, which means that du is 8 dx, which means that dx, which is what we have, is 1/8 du, right? And then we end up getting something like this, right? We've got our dx is our 1/8 du, and on the bottom, we've got a square root of 1 minus u squared. So that looks good, right? That looks just like our arcsine, right? Where a is just 1 in this case, right? I could write that 1 as a 1 squared, same thing. Okay, good. What do I have to do to my limits, though, then? Because this is a definite integral, right? So I converted from x's to u's and made the integrand look good. Yeah, I've got to go through my substitution and convert the x's to u's just using this conversion, right? There's my substitution formula. So when x is 1/16, what is u? One half, right? Yeah. You get 8/16, which is 1/2. So this guy is going to turn into a 1/2. And when x equals square root of 2/16, u equals square root of 2/2. Okay, that's much better, right? That's a definite integral that we can do without too much trouble. So this part right here then is just going to become, that just gives us our arcsine, doesn't it? Right? So we end up with 1/8 times arcsine of u evaluated from 1/2 to square root of 2/2. And this is just unit circle stuff, right? So if we look unit circle, oh no, is this gonna, I think this is gonna stop on me here. Oh my goodness. What's it doing? I think I gotta restart it. Shoot. Okay, so then, yeah, this is just unit circle stuff, right? So let me redo that. So if we look at unit circle stuff, if we're dealing with an arcsine, what's the principal domain of a sine function in the principal range of an arcsine function? What quadrants are we dealing with this in? For sine, no, it'd be 1 and 4, right? Because we have to be able to have all of the output values from -1 to 1. And we always want to have quadrant 1 because that's the most convenient, right? So it's 1 and 4. Okay, so in quadrants 1 and 4, where is the sine of what angle is square root of 2 over 2? No. Oh, hold it. Sorry. Yeah, pi over 3. You're right. Yeah, hold it. No, pi over 4, right? Pi over 4. Yep. Pi over 4. So we're right here, right? That's pi over 4. We get coordinates square root of 2 over 2, square root of 2 over 2, right? So sine of what angle is 1/2? No, pi over 6. Yep. Pi over 6 down here is going to give us x coordinate is going to be square root of 3 over 2, y coordinates 1/2, right? Okay, so then here, let's put some, so this is pi fourths and this is pi sixth, right? Okay. So then what's this going to give us, right? So this gives us 1/8 times the arc sine of square root of 2 over 2. You guys just told me that's just pi fourths minus arc sine of 1/2 is pi sixths. So what's that give us? Pi fourths minus pi sixths is what is that? 3/12 minus 2/12, so 1/12, right? 1/12 pi times 1/8 is pi over 108, I guess. Right? If I just simplify all that, right? Okay. That was a lot easier to do though than, right? I mean, than trying to convert back into x's. We just flip our limits and we're good. Make sense? Okay. All right. So for today, I want to show you guys, we don't really get into any of for the A/B test, we don't really get into any of the real heavy duty techniques for integrating. I do want to show you guys a couple of those though, but we'll do that kind of at the end at our leisure, right? I want to show you how to do integration using trig substitutions. That's a big one that you'll see in college. Using probably, I don't know if we get to partial fractions or not, but I want to show you just a couple of these, like integrating by parts, and there's a few of these that I think it's good to know before you go to college. At least have had some exposure to. But pre-AP test, we really don't do much. All we do on the AP test really is pretty limited. They just do U substitutions and then some stuff like this, where we're not really using any sophisticated techniques. We're just using a little bit of algebra to get the integrand to look good. So there's a couple techniques we can use that are very useful. One of them is completing the square. So whenever you have quadratic trinomials, so they're of the form ax squared plus bx plus c. Those can cause problems in integrands because they've got multiple terms with x's in them. And sometimes that can be an issue, right? Because if you try to take the derivative, like if we let u equal some quadratic trinomial, then du is going to be a little problematic because I'm going to have an x term and a constant in it, right? And so a lot of times that makes things difficult algebraically. And we'll see some examples here. But frequently what you can do is just complete the square to make that look like, and then make a u substitution. So it only looks like one term that has a u in it and one constant. So for example, how do we complete the square? Let's just remind ourselves how we do this. I did put up an optional 5-problem assignment that you can go in and look at if you want to on completing the square. You probably don't need to, but if you want a little bit of practice, it's there. So what do we do when we complete the square? You remember we went through this in Algebra 2. You guys probably did this a bunch last year too, I'm hoping, in pre-calculus, right? You have to factor out the coefficient of x squared, because the part of the expression we need to work on when we're completing the square needs to be x squared plus some constant times x. And that could be a negative constant or a positive constant. So we factor the a out of the trinomial, out of the first two terms, which gives us x squared plus b over a times x, and then the c we just leave out there. And then remember what our little trick is. When we're working inside these parentheses, if we want to create a perfect square trinomial, all we have to do is add to those two terms half of the coefficient of x squared, right? Half of the linear coefficient squared. So in this case, b over a is the coefficient of x, so half of that is just b over 2a, right? So we're going to add that quantity squared, but we have to use, we can't change the value of the expression. And normally we multiply by 1 because that's our multiplicative identity, right? Very infrequently do we add 0, but that's what we're doing today, right? We're just going to add 0 in the form of plus b over 2a quantity squared minus b over 2a quantity squared. But we're only going to group these three together, right? Because if we look at these three terms right here, they form a perfect square trinomial that's going to factor into x plus b over 2a times x plus b over 2a if we find magic numbers. So this all just gives me this every time, right? Okay, then we've got this additional, we already have a c out there. We've got this other term that we've subtracted that we're just going to lump with the c. Now I do have to distribute the a, did it again. I have to distribute the a because notice that the a is still factored out of this perfect square that we factored. I'm going to have to distribute that over to that term when I kick it out of the brackets. And so it cancels one of the a's that's being squared on the bottom. So when I square this out, I get b squared over 4a squared times a cancels out one of those a's in the denominator. And I just get this term, right? This looks a heck of a lot more complicated with a's and b's and c's than it does when you're just dealing with numbers, right? So let's look at a quick example. Like, what if we want to do something like this? If I want to rewrite this expression by completing the square, what do I do first? Factor out the -3. Just out of the first two terms, though, right? I can leave the constant out there. That one, we don't need to work with that one. So factor out the -3, which gives us that. Agreed? Okay, what's next? How do I create a perfect square trinomial? I add 0 in the form of what, though? Half of 5/3 squared, exactly, right? So we're going to have, we've got our -3 times the quantity x squared plus 5/3 x, and we're going to add half of 5/3 squared, and we'll turn right around and subtract that also, right, inside the brackets. Well, 5/6 quantity squared is just 25/36, right? Okay, so then we'll lump these three together. What do they factor into? What is this trinomial, those terms right here? What does all this stuff factor into? X plus 5/6 quantity squared, right? It's going to factor into that. That's a perfect square trinomial. That's going to factor like that. Okay. Then we just have to distribute that -3 over here. I might have messed this up. That should be a plus sign, shouldn't it? Yeah, that should be a plus sign. Just saw that. Okay. And so there you go, right? We just end up with -3 times x plus 5/6 quantity squared plus this constant. What would our u substitution probably be here if this was inside an integrand? Yeah, it'd be that, right? U would just be x plus 5/6. So what we're typically going to do when we use this technique is we make the u substitution u equals x plus b over 2a, right? And we end up with a much simpler expression than our trinomial. We end up with a times u squared, only one variable, plus some constant, which just ends up being the c minus, all that stuff right there is just our constant. Yes, sir. Because that's our recipe for creating a perfect square trinomial, right? I have to add the extra term. What I'm really doing is I'm I'm setting this up so these first two terms, now I'm able, because the coefficient of x squared is 1, I'm easily able to add the correct constant to just create a perfect square trinomial. Okay, so let's look at this in the context of a problem. So what about one like this? Okay, now if we look at this integral, you see the problems here, right? Like if I just start with that integral, what's the problem with just setting the bottom equal to u? Right? Like if I were to make the substitution here, if I were just to start off by saying, let's let u equal the denominator, x squared plus 6x plus 12, what's the problem with that? What do we get for our du? Yeah, look at that. Our du equals 2x plus 6 dx. We don't have that, right? And it's really difficult to complete this substitution because, you know, this is a quadratic function. So if I've got to solve for x in terms of u to complete the substitution, yikes. I mean, I'm going to get multiple solutions, right? I'm going to get a positive and a negative solution. That just looks like a total mess. And as you can imagine, it's going to make that integrand look so complicated that it's going to be very difficult to deal with that integral, right? So this is not a good option for us. We need something different. Okay, well, what could we do here? Yeah, let's just complete the square in the bottom, right? Now, this is an easy one to do because a is equal to 1. So what's the number we would have to add to x squared plus 6x to create a perfect square trinomial? 9, yeah. Right, so we're going to add 9 and then subtract 9. So we're adding 0. So don't we just get that? Right, this whole thing right here, isn't this just equal to 0? Right? And then we'll group those three terms together as a trinomial, and what do they factor into? X plus 3 quantity squared. I did it again. Oh, no, I didn't. What did I do? I don't know what I did. Right, so we get that, right, on the bottom. And then negative 9 plus 12 is just 3, right? So that factors into that. Make sense? Right, that's just 3. Why would I write it this way, though? If I make my u substitution, u equals x plus 3, then du is just dx. Look, there's a clean substitution. And then we're just going to treat this like a is the constant square root of 3. And which form does that match? Which inverse trig function does that match then, if I write it like this? Arctangent, yeah, sure, right? That's just equal to 1 over a times the arctangent of u over a, right? So that gives me that, right? That's our standard form that's right on your sheet. And now we just have to reverse our substitution, plug the u's and the a's back in there, and we just get that, right? Okay, make sense? Questions? See if you can, let me scoot up here a little bit so you can see all this. Questions in that process? Yes?
You just caught me off guard where like we had to like, can you scroll up a little bit?
Sure.
Where the box is at, why did we come to the conclusion of that?
What, this box right here?
Yes.
Well, because we can't change the expression, so we have to either multiply by 1 or add 0, right? So we're adding 0 in the sense of it's just going to be 9 minus 9, right? But we're going to group the 9. We need the 9 in here, because that's going to factor into that. See what I'm saying? And then the other -9, well, that just gets lumped with that constant. And the constant ends up being whatever it is, right? In this case, it ends up being 3. Okay, but it enables us, once we write it like this, now that enables us to do a u substitution that's going to work, because now my u is just an x plus 3. It's not quadratic, right? So you're probably thinking, okay, how would I ever know to make that step, right? You just do. I mean, that's because when you see a quadratic trinomial in an integrand, if it doesn't work with the traditional u substitution, which it might. I mean, what if we had something up here like on the top, if we had something like, x dx, then we maybe could have made this work with just a regular u substitution, but we didn't have that, right? So we're really stuck having to complete the square then to get to a point where there's a workable u substitution for us. Okay, and that's just something you kind of, when you do lots of calculus, you just start to develop that intuition, right? If the bottom is a quadratic and the top it doesn't have any x's, I mean, that's a pretty good indicator that you're going to want to complete the square. Okay, don't think that everybody that does calculus always gets this right on the first try either. It doesn't work that way. I mean, a lot of times you just know that this is an option and you try it and maybe it doesn't work sometimes. You move on to something else, right? But we know we're stuck. There's no u substitution that's going to work for us. So we got to move on to plan B. And this is a good option for a plan B. Okay, let's look at another one. Questions on this one? Okay, let's try another one. Okay, how about this? Here we go. Here's one with an x dx in the top. Okay, so this one looks a little bit different. Now, what's our goal? Our goal here is we want to be able to create a du in the numerator that's going to match the u that we would pick in the denominator, right? So what would be a convenient u for us to pick in the denominator? I'm going to do the same problem twice. We're going to look at it two different ways. What would it be? I mean, like if we're not going to, let's just see if we can avoid completing the square this time. Like what would we like u to be here? Say it again. Well, how about if we just pick the whole thing? Right? I mean, like if we just pick the whole denominator as u, let's just see what happens. And I mean, we've already talked about this a little bit. So if we pick that as u, then this becomes our du, right? So what could we do algebraically? What tricks could we do here to make the top look like that? Right? How could I turn x into 2x plus 6? Well, I could get a 2x by multiplying by 1/2 times 2, right? Isn't 1/2 times 2, 2x, right? So couldn't I do something like that, right? I'm going to multiply by 1/2 times 2, and the 1/2 I'll just pull out front. It's just a constant, right? So I've got 1/2 times what? How about that? 1/2 is being multiplied by everything in the brackets. Technically, the 1/2 is really, it started off right there. But because it's being multiplied by the entire bracket, we might as well just pull it out front. It's just a constant multiplier, right? So we'll pull that out front. And what have we done here? Well, we've multiplied 1/2 times 2x plus 0. You guys tell me, what's 1/2 times 2x plus 0? Isn't that x, right? Isn't that what we started with? Okay, so we know this is going to work because that's all we did was we just rewrote x in that form. But the 0 we're going to write as a plus 6 minus 6. How come? Because this is what we want, right? That's our du. Everybody see that? That matches our du perfectly. And so then all we have to do is, if I can write the top as a sum of two different terms, one of which is du, then that makes this problem a little bit easier to deal with, right? Because now we can do, you know what, I'm just thinking about this. So there's my minus sign. Oh, darn it, don't want to do that. I want to do this. Right? So we could do something like that, couldn't we? Everybody see that? Okay.
How did you get, how did you know to turn that
into 2x plus 6 minus 6? Just because I know I want to get, like the thought process here is that I want the top to match my du. So what do I have to do to turn that into a 2x plus 6 times dx? Well, just that, right? I'm just going to multiply by 1 in the form of 1/2 times 2. And then I need to get a plus 6 there. So I'm just going to subtract 6 also, because that's a 0, right? Those are just little algebra tricks that you can do to rewrite the form of something so it matches what you need. Okay. There's going to be maybe an easier way. Like when we just do this with straight up completing the square, I think you're going to agree it's just easier to do. Okay. So then what's left? Okay. So now we get this guy, which is no big deal. That matches our u substitution. We've got this 1/2 that I have to distribute. That 1/2 is being multiplied by the whole numerator. So I'm going to have to distribute that to this part and this part, and I can separate those integrals, right? So 1/2 times -6 is just -3. And then how do we deal with that one? Well, that's what we did last time, right? That's the same integral we just did. So all the stuff we just talked about, we could now do with this guy. See what I'm saying? That's a form that we already know how to start with. So this is just one approach to solving this problem. Right? Now this guy we can deal with. That matches our u substitution. This guy over here is the one where we would set that, we just did that one, right? But we'd have to go through all the steps that we just did also. It was almost that exact problem. Might have been slightly different, but it was that form. Okay. Oh, and then I don't think I ever reversed the substitution here, right? That ought to be this first one then. This really should be 1/2 natural log of the absolute value of, what was our u? X squared plus 6x plus 12. Minus square root of 3 arctangent of x plus 3 over square root of 3, and then I just lump my constants together. Okay, that's one way you could think of it, but wouldn't it really just be easier just to complete the square, right? Don't you think? We've got this thing on the bottom. If we just complete the square, what do we get? On the bottom, I'm going to get x squared plus 6x, what? Plus 9 plus 3, right? And there's my perfect square trinomial, right? So I just completed the square. All I did was I just completed the square on those two terms to get that part. Oh, darn it. Okay, everybody good with that? Right? Sort of, kind of, maybe?
Yeah, I get that.
Okay, so now we would rewrite this as we'll factor that perfect square trinomial, and we get the integral of x dx over x plus 3 quantity squared plus 3, right? Now, what's our natural u substitution here? X plus 3, right? That's a pretty clean substitution, and it's easy to reverse because it's linear. Are you starting to kind of see some of these little connections that are useful to us? So if we do that, I can easily, if I want to, just turn that around and solve for x also, right? Because it's not quadratic, it's a linear relationship. So if I get an incomplete substitution, which I'm probably going to, because look at that x right there, right? It's easy for me to turn those into u's conveniently. Okay, what's du? Yeah, dx, right? Good. And so here, let me do, just so we can really follow. Does the color coding help? It seems to me like that would really help. I always try to do it that way. Do you guys use that sometimes? I mean, so you can kind of see what the progression is. This part leads to this part. I just feel like that's got to help a little bit. So if I solve for x here, then, oops, let's make this green. So there's all my stuff that we're using to substitute. And what's this thing become then? So this looks like the integral of x, which is u minus 3, times dx turns into a du divided by u squared plus square root of 3 squared, right? Okay, now what? We completed the square. It's looking a lot better. What can I do here? Any ideas? Does that have to be the right idea? I mean, you're just starting this stuff, but any ideas what we could do?
Does the top have to be one?
No. Split it. Yeah, split it into two different integrals, and each one of those looks doable, right? If I split this thing, because I've got multiple terms in the numerator of my integrand, split it up, right? So now I've got the first integral is the integral of u du over u squared plus, and I'll just leave it as a 3. Just leave that one as a 3, minus 3 times the integral of du over u squared plus square root of 3 squared. Okay, that one we know. What form does that match? Arctan, right? Yeah. So this guy over here is just going to be 3 times 1 over a, so that's 3 over square root of 3 arctangent of u over a, right? Plus we've got some big constant that we're going to, all these things contribute to a constant, right? And then we can just reverse that substitution and we got it, right? U just becomes what, an x plus 3? And that guy's done. And 3 over square root of 3, isn't that just square root of 3? Right? So this whole thing over here just becomes minus square root of 3 arctangent of x minus 3 over square root of 3. Okay, what about this guy? How am I going to do that one? That's not a standard form yet, right? But could we do another layer of substitutions? Could we do a v substitution? What could I substitute here? Okay, yeah, look right here. What if I said for this guy, what if I made the substitution, let's let v equal u squared plus 3. Then what is a new color? I guess we're going orange. What is dv? 2u du. Look at that, that matches. 2u du. Well, we've got a u du, which must equal a 1/2 dv, right? There's no reason we can't do another layer of substitutions. The u substitution clearly helped. It made things simpler, but we still need another one because that doesn't yet match a standard form, right? But if I make this substitution, this guy is just going to become the integral of u dv, isn't that just a, or u du, that's just a 1/2 dv divided by u cubed plus 3 is v. Okay, that's the standard form. What's that equal to? Natural log. Yeah, look at that, right? That's going to become 1/2 natural log of the absolute value of v. But look, that's v is always positive, isn't it? Because u squared plus 3 is always positive. So we don't even need the absolute value there. It's just natural log of u squared plus 3, right? And then one more step to do. We just plugged in our v, right? This whole thing is v. It's natural log of v, and we just plugged it back, plugged the u's back in. Got to go one more step though. I got to plug the u's back in, right? So what was u? U was x minus 3, right? Isn't that what it was? Yeah, x plus 3 should have been. Whoops. So let's fix that. That should have been a plus right there. So this is now going to be 1/2 natural log of x plus 3 quantity squared plus 3. Then we got that other part, right? And if I want to, I could expand that out. And what do you think I'm going to get if I expand that out? X squared plus 6x plus 9 plus 3. Right, if I expand that whole thing out. There it is, right? I mean, if I see, all I did is just expand that out. Okay. Is it an accident that we got that? No. I kind of would have expected that to happen.
That's the original equation.
Well, that's the original denominator, right?
So
Okay.
why does that happen?
Why does that happen? Well, I mean, because that happens because that happens, right? Right? I mean, look what we got. And that doesn't need to be, it turns out that probably doesn't need to be in absolute values because it's always positive valued. But
Oh, that was like right.
yeah. I mean, because we got a natural log out of this. Well, the natural log came from the fact that we have this. I mean, so you can kind of expect that's going to happen. Maybe after you do this for a while, you'll sort of expect that that's probably going to happen. The more of these you do, you just kind of intuitively, you'll just see that coming. It takes just some practice, but okay. So I know we're running out of time here. Are we at like 1 minute or something? What would we do there? I can't really pick a DU, can I? It doesn't match. But what would my strategy be? I'm going to complete the square in the bottom, right? If I complete the square in the bottom, that's going to end up looking like the square root of a squared minus u squared, right? And then that starts to look like an arcsine, okay?